All right, so let's look at the magnitude of this force. Right? We talked about its direction, what it is generally from microscopic perspective, and what is this reactive force that is trying basically to prevent whatever motion we're trying to cause. Right? Let's talk about its magnitude. It's a force, it has a direction, it's magnet and a magnitude. Now, the way we calculate the magnitude, or we at least come up with some expression for its magnitude, depends on really what state we are, what the state or object is. So there are three possible states that a rigid body can be at any given moment, right? Typically, at least in engineering mechanics. Our body can be in equilibrium, right? This is basically what we've been dealing with, right? Equations of equilibrium. We talked about static equilibrium, basically when the object is not moving, or its equilibrium means when it's also moving with constant acceleration, right? Now, when the object or the rigid body is in equilibrium, it's pretty straightforward because nothing is moving. So we can just find the moment about a specific point and use that to find the relationship between where this friction has to be, right? The x value, you can actually find that x value easily. Knowing the weight of the box and the force P trying to make this box move, or any rigid body to move, knowing all the forces and where those forces are applied on your rigid body. So uh, knowing the all the forces, right, and the geometry, you can most of the time easily find where should this normal force be, better to say, right, on your rigid body. The second case is when we have impending motion, and this last case is when we actually have motion, when the object or the rigid body is moving. Let's just go over them one by one. Let's just start with the first one, right? Let's put it as 1, and that I'll go with equilibrium. Well, let me write one line at least here. The body can be in one of these three states at any given moment. Right? First is, let's start with the simplest one, equilibrium. So your body could be in equilibrium and it's not about to move, it's not moving, it's just sitting there pretty much. The rigid body is moving, it's sitting there. In that case, knowing the geometry and knowing the forces, you can find out where you have to put your normal force. Right? So what I'm trying to say is that let's just go with the box example. Right? It's a rigid body. Let's put a W there. Well, W, we put it, is applied to the center of the mass, so in the middle. Let's say the box has the width of A. So this is going to be, there's a different color there. This is going to be A over 2, A over 2. I'm assuming the width, the size of one side of the box is A. So A over 2, A over 2. And let's also say we are applying this force P somewhere that is H above the surface. All right, if this is the surface, let's say this height is H, and this is P. Right? Force P is applied somewhere on this box. As I told you, think about when you're pushing a tall box. If you push it all the way from the top, it flips over, versus if you push it closer to the bottom, it starts moving, right? So it matters where you apply the force, and that determines where to you have to put the normal force from the ground, right? When you have contact between two surfaces, full contact. So, and we have clearly the friction, right? This is friction somewhere. It's in this direction. And we have normal force. We don't know where to put it. I'll just put it somewhere. And that's the whole idea. You want to find out where should be put. And let's call this distance x, right? It's x away. I take the center of the box as my reference, and I want to know where should I put my normal force if force P is applied at some height. Right? Closer to the top is different from closer to bottom, right? You'll see that actually affects. Now, how do I find that x, or the relationship between these forces and normal force and x? Actually, you can easily find if you find the moment about the point, let's say I call this point the point of the point I put F and N, right, wherever it's applied, let's call that point O, some point O. If I find the moments about point O, let's take this as positive, right? F passes through O, N passes through O. So F and N are out of the picture, right? We said it's friction. We don't really actually know how much is that. When we're in equilibrium, friction is an unknown value. You will see later on when we are in impending motion, we're in motion, we actually can come up with an expression for the magnitude of friction. But when the object is sitting somewhere, it's not moving, even though you're applying some force to it. If force is not strong to make it move, friction is an unknown force. So magnitude of friction, let's phrase it this way, magnitude of friction really depends on which state you are. As I said, could be there are three possible states at any given moment for an object, for a rigid body. State one, equilibrium, the magnitude of the force is unknown. Magnitude of friction is unknown. It's some unknown that you have to find from your rigid body. So you're adding an unknown to your free body diagram. Treat that as an unknown. Now, you can find where x is without knowing that unknown. Right? If you find the moment about point O, in this case, for instance, F is an unknown passing through O, so you can get rid of that. N passes through point O. You only have W there. This is W. And you also have P. So if you just write, that would be W times X, right? And it's positive, minus P times H is negative, is equal to 0. So from there you can actually find x. If I can write in a better way. From there you can find x. X is PH over W, right? So you could find x once, if you know PH and W. Once you know x, you can also find other unknowns. Summation of force in x direction, summation of force in y direction. Just remember, when you're in equilibrium, I put it here. Friction is an unknown force. Right? We don't really have any expression for that. That's what I meant. This is when the rigid body is not moving. Right? The second state, well, let me be consistent. The second one is called impending motion. Now, what impending motion is something interesting, that your rigid body is still not moving, right? It's still in equilibrium, but it's about to move, right? So there is a fraction of second, I would say, maybe a millisecond or shorter, that the force you're applying is getting to, let's say you start applying a force to an object, your rigid body, and slowly increase the force. There is a fraction of second, there is a moment that after that moment, your rigid body starts moving. That moment is called impending motion. That's the state. That's the state that your rigid body is in. So, impending motion. Impending motion. Right? In this case, in this state, you actually can come up with, there is a relationship for relating friction at this specific moment and normal force, right? So let's think about it this way: as you increase P, force P, F also increases. Right? You have friction, you have P. As you increase P, obviously first is also, F is also increasing because your box is not moving, right? So this force F is still strong enough to overcome the P force to make sure that the box is not moving. So as you increase P, F increases friction, right? It's always trying to stop the motion, so it keeps doing it until at some moment this P reaches a certain maximum, or let's say F reaches to a certain maximum value. We call it F, related to static friction. Fs usually we represent that. Now, this specific value, the value of friction immediately before your rigid body starts moving, is proportional to normal force that is applied to your rigid body. So if I draw it here like this, so if you have your rigid body here, we're just going with this box we started our example with. So this is your W there. You have your force P is increasing, right? At this point, your impending motion, so it gets to a point that your rigid body is about to move. Now you have your friction here. We call it Fs when we are in impending motion. And you have your normal force there. And this is X. X you already found. From up to this moment, it's still the same. It's not moving, right? And you found the moment about point O. So F increasing, being increased, or N is increasing, doesn't really change anything. The only thing that changes is P. So by changing P, X moves. But you still know how to find X, knowing P, H, and W in this case for this rigid body, for this box. Now you're at that point that this was height was H. Nothing changed at this in this case. It's still H above surface, right? Just increasing the magnitude of P. So here's what I write: as P increases, F correspondingly increases. These are for a separate topic, right? So let me, there you go. F correspondingly increases until it reaches a certain maximum value, which we usually show that with Fs. Right? Now this value is directly proportional to the normal force. If you want to write this as that reactive force, this would be your reactive force here. And let me show you the same color I showed you. This would be your reactive force. R. So your Fs is equal to mu s is a constant n. This is the expression for friction when you're in impending motion state, meaning that immediately before the motion starts. Right? And here mu is, let me put the names here. Mu, we call it coefficient of a static friction, right? This is a static friction. That's why I show it with S. So coefficient of static friction, right? And the angle also, this R creates with normal force, they represented with theta S. You can also find theta S. Theta S is basically tan inverse, if you know these two forces, is Fs over N. And since you know what Fs is, we can actually write it as tan inverse mu s n over N. That'll be tan inverse mu s. Now, what that mu s is, this coefficient of a static friction, is actually constant. Right? There's also a name for this angle. We call it angle of a static friction, if you want to be more accurate. Angle of static friction. All right. What this mu s is? This mu s is basically the is a constant that they calculate that you are given. They calculate this using experiments. How do they do that? They put two surfaces of different materials with different type of finishing in terms of manufacturing, and they measure the friction between these surfaces. Let's say you have a box 10 kilogram, put it on a surface made of glass. They pull it and they measure the force at the moment before the motion starts, right? So they start increasing the force and suddenly the motion starts. So whatever the force was at the moment before, a fraction of a second before the motion starts, that's Fs, right? Because that's exactly how P should be to overcome this, to make this happen. And then knowing the N value, which is normal force equal to weight, they can find coefficient of a static friction. They're usually tabulated in different books, so we can actually look them up depending on what type of surfaces you have. If you have a wood on a glass, you have wood on a wood, you have metal on ice, right? There is actually a table in your book. There you go. I actually took this from your book. So as an example, here are some values for, I think it's from your book. Here are some values, typical values for mu s, coefficient of static friction. They found it by experiment. So if you have metal on ice sliding, your coefficient of static friction is somewhere between 0.3 to 0.03 to 0.05. Changes all the way to copper on copper, right? So very high frictions between 0.75 to 1.21. It's a range, because it depends on the finishing of the surface of the copper and the way they did the manufacturing. But so this mu s is something that either you're given enough information to find, or it's something that actually it's given to you, because they usually do this, find this coefficient through experiments, by running experiments. So you can estimate these values. So in this case, Fs actually has an expression, as opposed to equilibrium state. In impending motion state, Fs, there is an expression for that, and you can actually calculate that. All right, given mu s, you can calculate N, depending on what the configuration of your rigid body is. You can usually find N, right, normal force from your surface. Knowing Fs, you can calculate mu s. Knowing mu s, you can calculate Fs. Right? So that becomes a known in your typically free body diagram. Or even if it's not, you're given other knowns, you're able to find mu s, depending on the way the problem is phrased or what you're asked to find.